Hello everyone. I think this is the last interactive session for us, and it's been a pleasure for us to be able to deliver uh, and interact with you guys. Okay, what we will have today means again like yesterday. What we will do, we will revise this. Means yesterday I completed kind of half and more than half of the revision, and the rest of will be revised today. And after that we will have some discussion, and after and the second part sir will take, okay, regarding few applications and other concepts. Okay, so hello everyone, I am Harshavinash Tanti, your post here. Okay. Currently I am a research scholar at Department of Astronomy, Astrophysics and Space Engineering at IIT Indore. Okay, now I hope everyone can see the screen. As we discussed yesterday about the radio band, and so there is a radio window due to which uh, we can observe space in different regime. So in optical, we have optical telescope. In radio band we have radio telescopes, and for if you want to observe at other bands, we have to go out of the atmospheric boundary of the earth, such that we can observe of our universe in those wavelengths. Okay, now going to I will skip the slides which we did in the last session. So we finished off with revising the observation techniques and some important formulas is using when we are using single dish telescope. Okay, single dish telescopes. Now, since till now, means till the week 5, I believe week 5 we covered some basic units in astronomy, like flux density, what is brightness, temperature, then what is specific intensities, all this stuff, and addition to that, at all the kind of hardware which goes into astronomy. Now, when we go to when we want to do astronomy, the first thing we need to know where the star is located at, right? To do a means do a observation, we need to know some kind of area or area of the sky which we are observing. So for that, we need to have some kind of measurement techniques or some kind of dimensional units to represent a particular region of the sky or particular star in the sky or particular source in the sky. Okay, so for which we have a coordinate system, just like we have a Cartesian coordinate system XYZ, and mathematically we have spherical coordinate system as well as cylindrical coordinate system, and then there is something called Euclidean space. Now there are different kind of coordinate system, but in radio astronomy we mainly use means the most used coordinate system is equatorial coordinate system. Okay, wherein the say we have this is what general diagram of equatorial coordinate system is. So we choose a fixed point at the vernal equinox. Vernal equinox is kind of a means if you create a circle around the sun and kind of intersect it between the equator and the pole, so and that intersection is termed as vernal equinox. It occurs twice a year. Okay, when the sun crosses the celestial equator. This is the definition of the vernal equinox. Okay, now you can kind of think of this in a way like you have longitude and latitude in Earth to represent any position of a user. So in the same way, if you extend that concept into the space, so you will have some kind of long and lat to show where the source is at. But this longitude latitude would we cannot extend this concept directly to space because it is Earth fixed coordinate system. Means it changes with Earth. If Earth is rotating, the longitude and latitude would will change for any particular source. So a new kind of coordinate system is invented equatorial coordinate system, where the declination is is your corresponding latitudes, and your right ascension is related means is assigned with respect to the vernal equinox times. Okay, so there are some things you should know. Uh, Means there are two terms in equatorial coordinate system, which is RA and DEC, right ascension and declination. RA is kind of, you can say, uh, a version, means represents a latitude in this longitude in this in this coordinate system, and it is in hours, minutes and seconds. It's the unit is in hours, minutes and seconds, and declination is kind of latitude in your coordinate system, and represented in degree is degree, minutes and seconds. Okay, so these are the units. And now this right ascension and declination is fixed for any source, means most of the sources outside our solar system, or the very far away are very far away from our solar system. So so that's there. So in week 7 you can find the more elaborated discussion about the right ascension and declination. And now there is something called LST. Okay, when you study any other coordinate system. Okay, now this LST depends upon the and the full form of it is local sidereal time. So local sidereal time is defined as as it should be 0 hours when the vernal equinox is on the observer's local meridian. Okay, now what is local meridian? Local meridian is, like, say you are here and you are this is south and this is north, and if you join this 2 point like this, so this is a local meridian. Now this should be 0 when we are we are at 0 hours, means like this meridian will point towards your vernal equinox point, this point. Say if you are here and if the local meridian is like this, then this is LST 0 hours. Okay, now with this there is something termed as hour angle, and this alpha is nothing but right ascension. Now these two terms, why this came into picture is the RA and DEC coordinate system is defined such as doesn't gets affected by Earth's rotation. Now the Earth's rotation period, we say it 24 hours, but it's not 24 hours. It's near around 4 minutes less than the 24 hours, because of which there is a there is a error in the 360-degree rotation, and which is accounted for in local sidereal time. So that's why local sidereal time and local time are different, because of the Earth's rotation is not completely 24 hours. So local sidereal time takes the exact hours for the Earth's rotation, and based on that, local sidereal time is calculated. And local time is just 24 hours, whatever we do right we have in our watches and all. Now this hour angle, what is hour angle? Say if you are watching any source, now if this is the Earth, and then what this is your declination, this will be declination, and if you and this kind of curves will be your right ascensions. Okay, so just like your latitude, longitude, this will be delta, and this will be alpha, means right ascension. If Earth is moving, this coordinate system doesn't move. Okay, this is fixed. Equatorial coordinate system is fixed, although Earth is moving. Since the Earth is moving, if you are observer somewhere say here, then you will move, and the earth is moved, then after some time you will reach here. Now here to here, you traveled an angle, okay, in terms of the greater sphere, you traveled an angle, so that angle is known as our angle. Now say this is your earth, this is your earth. Now you are the observer is here, and due to the earth motion you reached here. So this is the amount of angle you covered, and which will be known as our angle. Okay, so there is a simple relation between local sidereal time and our angle, which is your LST is equals to what? RA plus our angle. Okay, so this is the simple relation you should remember, because when we do analysis, we tend to plot in terms of LST, because in terms of LST, source is mostly fixed in the equatorial coordinate system. Okay, now there is means you can this is let's move on to the next coordinate system. The next coordinate system in galactic coordinates, where the sun is the kind of the center for the coordinate system, means origin in, and the 0 degree is towards the galaxy center, means our Milky Way galaxy center. Now from there, the similar lat-long type of coordinate system is generated, and the both L and B said that longitude and latitude, or galactic longitude and galactic latitude, are in degree, minutes, and seconds. Okay, so this is also used for kind of if we are observing with respect to suns. Say if you are doing a study where sun comes into picture, the mostly mostly used positional coordinate, or the coordinate system, is galactic coordinate system. Okay, so now before moving forward, what is the importance of learning this kind of coordinate system? Okay, the thing which we did, I am not revising it here, you can view it in the 7th week, is that there is coordinate transformation defined for this based on trigonometric functions. Now, this galactic coordinate system or the equatorial coordinate system can be translated to lat long, and the most important thing which we require is azimuth and elevation. Okay, azimuth and elevation. Say if you are using an antenna, you have say you have an antenna. Okay, elevation is the angle required. You need to take means the angle for antenna you move in the kind of a horizontal vertical in vertical angle. Okay, the vertical way, and azimuth is the horizontal rotation. Okay, so if you want to point any source at a particular RA index, you should know about azimuth and elevation. There are several apps also, like Star Tracker, Stellarium, and this type of apps which can show you the azimuth, real-time azimuth and elevation of different sources. But to calculate this, you need to use the cosine cosine formula, which is discussed in the 7th week. Okay, now this thing is very important because we need to go back and forth into LST calculation as well as your coordinate transformation calculations. And if we miss by a certain degrees of values also, we can and because of which we can miss the source which we are looking at, because the more sophisticated interferometers have very arc second resolution. So if you are If your error is between few arc second, that means you might miss your source. Okay. So this is why we require this coordinate system and the knowledge of coordinate system very well. Okay. Now moving towards in the week 7 itself, uh, we have basic interferometer where there is two, and means if we to realize this, we will see is we will think about is uh, say we have a single dish of 100 meter, and for simplicity's sake, I will take 20. We are observing 21 centimeter line. Okay. Now with this is what will be the angular resolution we are looking at. It's roughly e 1.22 into your 0.21 by 100. Right? And if we ignore this, so we will have 0.0021 radians of resolution. Okay. Now, if we want to detect even finer source, like which is in few milli arc second, what we will have to do, we have to increase the dimension of the antenna. Means the resolution or the angle theta is inversely proportional to dimension of the antenna. Okay. So if you want to do observation at a particular wavelength, we need to increase the dimension of the antenna bigger and bigger. So, and there is a practical limit on the how much big antenna you can make. Okay. You can't make 100-kilometer antenna. So using the array theory, we got to know that we can use array theory in antennas. We can use multiple antennas separated by a distance to emulate for a bigger dish antenna. Now, this put forward the concept of basic interferometer, where we have two antennas separated it by a baseline B. Okay, and that is correlated. Okay, now what happens here? If you have two antennas separated by a distance, if there is a source up here, it will reach the antenna at different time, and that time required is given by tau. This tau beta, tau baseline, this is baseline, and sine theta over c, which is speed of light. Now, because of this and the principle of means Young's double slit experiment, basically, you will see that this causes a kind of sinusoidal wave. If there is a kind of a coherent, means a single source out there, so you will see when you correlate these two, you will find a sinusoidal signal, or the which you can term it like this, that if you have a single source in the sky, it will create a kind of a sinusoidal pattern, or you can sample the sky in this direction. Say, sample the sky in kind of a sinusoidal pattern. So instead of having a single, or you can say instead of having a single beam, you have like a multiple beams here. So you can sample the sky like this. But this thing also has a limit with its field of view. The field of view of a basic interferometer is defined by the diameter of individual antenna. So what you will have one bigger field of view, and in which, due to the interferometry, you will have a smaller resolution beams. Okay, so like this. So you can means see where I am going at with this. So using two antennas, we can sample sky horizontally. So if we have another antenna over here, so the number of baseline increased to 3. So with 3 baseline, we can sample it in another way. Now, the thing to note here is the baseline. So the thing you should keep in mind when you are doing interferometric principle, redundant baseline will cause same pattern. Okay, so there should be minimum redundant baseline, or there should be no redundant baseline in some cases. Redundant baseline will have you won't be able to figure out which phase or the which signal variation is from which baseline. Okay, because both will generate same kind of pattern. And if they are in the same location or the same direction, means direction kind of thing. Say you have a baseline here and here you have another antenna which is also B. Now you won't be able to figure out, if you correlate these things, these two signals, you won't be able to figure out which is from uh, means what information it is adding in. So in the same line, you can't have a redundant baseline. So if you have an antenna here, you can have a baseline here, but although the baseline will same, but the baseline vector is different, which will have a different UV coverage in the UV plane. So now I termed a thing called UV coverage. Now UV coverage is what uh, is is uh, is due to your rotation of the Earth. Now, if you have a means antenna structure over Earth, like say you have 2-3 antenna like this. Now Earth is rotating. What will happen? And you will sample the sky. The sample sky will be sampled like this, and the means these two, for these two baseline, it will be sampled like this. For this two, it will be sample means these two, if it samples like this, and this two will sample like this, and there will be a different UV coverage, like you will sample the sky in a different way due to the Earth's rotation. Now with this, then you have a something called sampling function, and means you means grid this UV coverage, and then do some point spread function, and those are means image processing, means creating an image essentially out of an interferometer, which is also known as rotation for Earth's rotation for synthesis imaging. So this is what synthesis imaging means. You have a set of baseline, and you means due to the rotation of the Earth, you means take advantage, means kind of you exploit that and take different samples in sky and make a image. Okay, now comes with interferometer comes a different problem, that we will have a multiple sensors and multiple systems. Okay, that multiple system will have their own system temperature. So for which the sensitivity of the interferometer will change. Now if you have multiple sets of antenna, the interferometer sensitivity equation is given by this uh, by this. So this is in a sense, it is very similar to your single dish equation. So this is the equation very similar to the single dish one. Now this here the extra term you will see here is the n. Here the n is nothing but number of baselines in the in your interferometer facility. Now this n minus 1 is nothing but your nothing but your arithmetic mean. Okay, so if you have n number of baselines, so what will be the total of that? N minus 1 by 2, I believe. This is the means the sum of 1 to n looks like, right? So by that it came into picture. Now if you see the sensitivity, it decreased by factor of kind of n to n minus 1. Okay, if you observe, if we see again this one, so here the sensitivity depends upon effective area and only the observed time multiplied with the bandwidth. Now, if you move towards interferometer, you see that your sensitivity is increased by a huge margin if you have n number of antennas in your interferometer. Now, provided that the system temperature for each antenna is maintained at the same temperature, here there shouldn't be any fluctuations. If there is the system temperature for each antenna is different, that should be accounted for, and that essentially is calculated as T1 square plus root over T1 T2 square, means like uh, uh, square root of the sum square of the temperatures. Because this way is kind of approximated that approximate system temperature. And there is two more terms over here, whereas which is Na and Nc, means eta A, eta C. These two are efficiency of of aperture efficiency and correlator efficiency. Now, as I said, if we have n number of antennas, we need to mix those signals or correlate those signals with each other. So for which the correlator efficiency comes into picture. How efficient is your correlator? And that depends upon your sampling speed of the ADC and the sampling speed of the ADC, and how sensitive your instrument is actually. So these things and the losses are considered like that. But the simple thing by which they account for all these losses or calibrate the system is by looking first at a calibrated source, means like a source which for which you have proper data sheet, how much the flux is, how much its phase is. So there is two types of calibrator: flux calibrator as well as phase calibrator, using which you can calibrate your antenna. Okay, if you just like you remember, if you remember the calculations we did for single dish here, the we means voltage calibration kind of thing where you have you can calculate the system temperature by viewing the calibrated source. Okay, now same thing you can do for your interferometer, and is being done when you are doing any major observation using means national facilities like GMRT. Okay, so in context to this, I think this was in a Wigton's assignment, and so let's do this again in this session. And so we want to detect an unresolved source at 22.2 gigahertz, where we have a sensitivity limit of 0.3 Jansky, and we did not detect the source. Now, if we use an array of 3 antennas, so all the systems will be at 50 Kelvin and has aperture of 30.4 meter square, observing a single polarization with bandwidth of 50 megahertz, and correlation efficiency is to be assumed 0.8. Now said that if we fail to detect the source, we would like at least to half the upper limit on the flux density. Half the upper limit on the flux density. Okay, so upper limit on the flux density is half, and the 5 times the RMS noise. So upper limit is half and RMS is 5 times. That means the total means gap should be around 10. Okay, the factor of 10. Now the factor of 10 comes into picture, then that means you need to be able to detect the sensitivity level of 0.3 Jansky per synthesized beam. Okay, and if you plug in the values into the equation, you will arrive at 119 seconds. And for about 2 minutes of observation. Now with that, with the same thing, if we do it for single dish, we will arrive at 0.05 Jansky. Now you can see the difference in the detection limit. Say for 2 minutes you calculated it for 0.03, and for single dish you have 0.05. So your sensitivity has increased, okay, in interferometer. Okay, this is because although you are using a smaller antenna, but what means you have increased the number of antenna, thereby increasing the total area. Okay, now if you have the comparable area, say for example, you have n element interferometer are having some geometric area, so for which you will have uh, you will have equation like 1 over n minus 1. Okay, sigma nu f nu is equals to proportional to this. Okay, now if you have and this is a geo. Now if you have a single dish of n times the geometric area, say this is for interferometer, I will term it as I, and single dish f nu, and this is s, will be proportional to 1 by n times your a geometric. Okay, whatever what I said is you have an interferometer of a geometric area of means n element interferometer of a geometric area, and on the other hand you have a single dish of n times the geometric area. Now if you do the uh, ratio of this, so sigma f I to sigma f nu s, what you will get root over n minus 1 n over n minus 1. Okay, so this, what does this represent? This represent that the sensitivity of the interferometer is almost equal to the sensitivity of a single dish interferometer having the n times of the area of a single dish of an interferometer. Okay, so if you have a single dish telescope, you need to have n times the area, whereas you can have a smaller dish and a small means n times smaller dish, and you can place it means around some area to create an n element interferometer, achieving the same amount of sensitivity level. Now these are the main key points you should know about when you are doing some kind of means radio means if you're dealing with radio instrumentation and this stuff. Okay, now after this something comes imaging. Okay, so in imaging, what you have, you do you utilize the rotation of the earth to create a UV coverage, mean to see how the n number of elements and the n number of baseline covers your sky, and based on that you create an image, which is also sir, in week 8 or 9, sir, in week 8 and 9, so showed something called dirty image, from where how we can remove the point spread function, how we can denoise it. There are different algorithms as in I think week 9, week 8 and week 9 and week 9 CASA lectures, week 8 and 9 CASA lectures. You can those there are some software tools, CASA, AIPS, apes by which you can uh, kind of analyze these interferometric data. Okay, so this thing actually sums up the entire instrumentation part of the instrumentation or instrument related summary of the radio astronomy. And there are different techniques by which you can do imaging and do uh, imaging, for which you can go through the lectures 8 8 onwards. Okay, week 8 onwards. Okay, so with this, thank you.